So next up is Guglielmo from University of Aberystwyth, who was obviously introduced throughout that presentation. So I'll hand over now.
Morning. I believe you see my presentation, yeah?
We can see your screen, okay, thanks.
Okay, cool. All right, hi everyone, I'm Guglielmo Persiani, and today I'm going to present a part of my PhD project, a research that I did in Aberystwyth University, which is about the biochemical characterization of fouling and corrosion issues in coal mine drainage. And as anticipated, we are in the South Wales coalfield, so we're dealing with surface drainages draining from abandoned coal mines. Of course, I would like to thank all the supporters of this research, my supervisor and my co-supervisors, and as well the Coal Authority, CAS, and the BGS to have supported both financially and as well the site access during all the PhD. So, as already introduced, and during this conference, I think this topic has been already touched, which is very critical, I think, is the risk of the corrosion and scaling in the coal mine. So we have a very common issue, which everyone, I think, potentially can recognize, which is the iron oxide scaling, which is why actually most of the coal mine drainage, and most of them, they are looking as ochre, so they look like orange. And this is a common problem, widespread. And as well in this precipitate, we can find also other kind of minerals like carbonates. We can have sulfides, and those issues actually can cause clogging in terms of heat water schemes. And as well, we can have other problems as corrosion. So corrosion actually is what can dissolve that metal's surfaces, and this, as clogging, can therefore impact the sustainability of the heat scheme. So that is the reason why we are looking at this. Is actually, as already mentioned, when we manipulate this water, we want to be aware of the risk it can provoke, and the risk of falling and corrosion is a very potential risk, and that's why this research is actually try to understand a bit better. So here we're looking at the biochemistry of those minerals and the corrosion issues in the coal mine water. So what is that? Is actually what we are asking here is if there is a role, and which are the interactions between microorganisms and mineral precipitated on the surfaces in contact with the mine water, and as well what is the role of microorganisms in the context of the corrosion. So to do that, we use anorganic techniques like SCM ADS, okay, so scanning electron microscopy, which is coupled with energy dispersive X-ray spectroscopy, which allow us to see and identify chemically the minerals on the surfaces of the material. And this is all coupled to X-ray diffraction, which is a well-known instrument, a well-known method to identify the crystalline phases. All this together with eDNA sequencing, which is actually informed about the diversity of the microorganisms living in the biofilm on the surfaces. And from the diversity, is also possible to speculate about the metabolism of those microorganisms. So actually here we are linking the diversity to the metabolism, which in turn means what microorganisms do with the water, which chemical they can produce, and so which reaction they speed up, which is critical for example, in the context of hydrogen sulfide or iron oxidation, which is actually both of them, one corrode and one can increase the rate of formation of iron oxides. So very, very quickly, how we did that. So how we retrieved the sample from the field. So we choose an approach which was in situ. So we build up a coupon, which can be seen as here like a sandwich. essentially what we did is to put different channels of different material, PVC, mild steel, and copper, between two plexiglass sheets, and then we closed them into a box which was holed to allow water flow across it, right? So then we closed this box and we incubated directly into the drainages. So in this approach, in our mind, was actually the most representative as possible. I mean, that's as far as we can possibly during a PhD. So we just, and this was kind of essential to try to retrieve samples that represent what actually form on the surfaces of the material and how the material looks like after 10 months of incubation. So to proper have a look about how things look like in the real condition. So I'm gonna start. I've during this coupon experiment, I've investigated 4 sites, and the choice of the sites has been, of course, arbitrary. Just we chose them, and we chose them because they're very different chemical, water chemical conditions. So we have iron-rich sites, which can represent the more classic coal mine drainage in the UK. So waters that is rich in iron, oxygenated, where probably the chemistry is driven by pyrite oxidation, and alkalinity is not very pronounced. So I'm gonna start talking about very quick about Inisarwood, which is a very iron-rich site. Concentration of iron is about 70 milligrams per liter, and what actually this show is the minerals that fall on the surface are identified as goethite and lepidochrosite, which are actually 2 iron oxides. But still, we can see that even in this orange ochreous material, which is again the classic one, we can find a good amount of structures which are actually the result of the microbial metabolism as the stalk formation. And in the bottom right picture here, we can see that those stalk style formation, they might represent the most of the ochre material that precipitate on the surfaces. So that's was very interesting to see that actually there is a magnitude of how much iron oxide microorganisms that can contribute in the scaling formation. In this side, just to mention, there is no corrosion issue. So classic iron side, we didn't find corrosion. And then we pass through Lindsay, which is still an iron site. So but here the concentration of iron is much lower, is between 10 and 12 milligrams per liter. And while the alkalinity is a bit higher. So on this side, we did find trace of corrosion, especially on copper, which the corrosion here after 10 months appear as a black thin slime on the copper surface, and this mineral is identified as chalcocite. At SCM, we can see this mineral on the bottom right of the slide. Essentially is copper sulfide, and which has a kind of flake mineral structure. As well, on this side, we did find interesting pyrite rhomboids directly precipitated on the channel surfaces, and as well sulfur as elemental sulfur, as we can see in the top SCM picture, which precipitate as in a euhedral crystal shape. So this is already something that we can already see many significant difference between 2 iron sites. But then let's go see what happens when coal mine drainage is not characterized anymore by high concentration of irons, but we change the chemistry to a sulfidic condition where hydrogen sulfide can be high as up to 25-30 milligrams per liter. So we have 2 sites here, which are Selinen North and Crumlin Navigation. So both of those 2 sites have both conditions that are very sulfidic. And in Crumlin navigation, this is very significant. It is up to 30 milligrams per liter, which is quite impressive to be also close to this water because it's very stinky. And we have also, just to mention, to buy gas mask to get close to it. So in this side, of course, we don't see any iron oxide precipitated on the surface because the iron under those chemical conditions do not exist as dissolved. Is already precipitated much earlier as sulfide. So the chemistry here is dominated by sulfide-sulfate couple, and the corrosion is very high. So we can see here the picture of the channel after 10 months of incubation. And of course, we did many replicates. We insert many replicates of copper channel into the drainage. And that was the only one we've been able to retrieve. Most of them, they just completely dissolved. And again, how they dissolve it is probably the copper just dissolve and then precipitate just right after as chalcocite. Okay, so that here we have a corrosion which is driven by hydrogen sulfide and which drive the dissolution of the copper in the first instance and then precipitate it out as copper sulfide. And this is very, in this site is very critical, but I think those sites are rare, so it's not a chemistry which is, is not diffuse, it's not common to find this kind of chemistry, but this hydrogen sulfide rich water, they might be representative of the deep mine water, as already mentioned by Angela earlier. So those sites might represent a good, a good case study, a good example of what we can expect in the most critical condition of the chemistry of the mine water, right? So what we can expect. So just to conclude this slide, we did find again pyrite rhomboids, which again has been interesting because pyrite rhomboids, it's kind of rare to find those good rhomboids just freshly precipitate on the surfaces. And this has been kind of surprising to us to find. And again, we did find sulfur precipitate as single element in usual crystal shape. So then what about the microorganisms living there? So the initial hypothesis actually was about, well, we're dealing with very different geochemistries here. So we are actually on the opposite sides of the geochemistries. We have one side iron, one side hydrogen sulfide. Together, they rarely exist. So if we have hydrogen sulfide, we barely see iron and all that. But then what we did find is actually there are a few genera that actually are common in all different sites of coal mines. And this has been pretty surprising. And those genera, for example, the sulfocapsa is a genus that is related to the sulfate reduction and dismutation. So actually these genus produce hydrogen sulfide. And this genus is actually common in all the sites, even in the sites where we have high dissolved oxygen and where we have iron. On the other side, we do have microorganisms like sulfurobum, common in all sites, which oxidize hydrogen sulfide. And so they actually represent, a common metabolic strategies, and they are common in all the sites, which has been pretty surprising to see. So I know I'm very late, and those are the conclusion. Hydrogen sulfide is extremely aggressive against copper and mild steel. And again, as I mentioned before, those conditions might represent conditions in the deeper aquifers. A good finding as well, very interesting, is that despite a significant difference in the geochemistry, we did find a genera, a common genus that dominate all the microbial landscape. And again, temperature affects the metabolism and the rate of reaction. So further research are required to understand what happened really when we change the temperature of the groundwater due to heat schemes. Thank you very much.